class. I'm happy to have all of you join me for this semester, for this wonderful class. Then my name is Wang Gong'an. Here is the office phone number, email, and the TA is Hugh. Raise your hand, Hugh. He is our TA. He's going to help me to take camera and monitor the close discussion, because he needs to submit some photos to EMI. So please cooperate with him. So, any question so far with my English? Great. Then I will put all our course PPT materials on iLearning. So you could go iLearning to get all the course materials. Course description, we will learn the microfabrication service from Taiwan Semiconductor Research Institute. We will use their fabrication process to design the device. You may or may not be able to submit your layout design to TSRI in May, but you will have some hands-on experience to analyze the chip, then to learn how to do some layout analysis, then debugging your layout before you submit your design to TSRI, Taiwan Semiconductor Research Institute. But anyway, you will register to TSRI to get an account. If you are lucky, you may be able to submit your design to TSRI. It will be a great experience, but we will see as the class goes. Kaiser, could you read this course description?
Introduction to microfabrication processes for micro electromechanical systems and the design of microfabrication processes. Chip design-based, industry-based fabrication facilities is the focus of this course. The course will include a term project.
Yes, we will have a term project for you. Probably you will draw your layout and to use the Virtuoso, the layout software, to do your design and to have fun with it. Okay, you will design a microsensor, and this microsensor can be fabricated by TSRI through their fabrication service. This is a textbook. You don't need to buy it because we have the PDF file on iLearning. You could download this textbook from iLearning. This is the book by Centuria to teach you the microfabrication fundamentals, the design analysis method of the sensors, and some case studies. So it's a good textbook for you to read. And the homework and final report. For the homework, I will ask you to do it in the class, and you can help each other to finish your homework. So you don't need to bring it home. You can just do it on the class. I will collect your homeworks on the class. And the final report is your layout, because you will draw a layout. So your final report will be your layout for your sensors. And bring laptop to class is not required. Yeah, you could do everything just by hand in a class. So this is not fixed yet, so don't worry about it. So if you take this class, you need to become the student member of TSRI. And if you need to do the chip design, then you need to register anyway. So go to this website and register as the TSRI member. Then could you, if you are not a member yet, are you a member? Not yet. But it is optional to register. It's optional, it's not required. So you should register, okay? So Marcy, have you registered? Okay, we can do that later. Then some reading you can do. So before we meet next time, please read chapter 3 of this microfabrication, the textbook, and do problems 3 to 1 to 3 to 4. Sorry, although for this one you need to do it at home. So any question with this? You can work together. You can ask questions. You can have someone in the class to help you for this homework. So at the beginning of the class, I will collect your answers. You don't need to do the PPT part. You can just do problems 3 to 1, 3 to 2, 3 to 3, 3 to 4. And give me your solutions at the beginning of the class next Tuesday. Any questions? Okay. So the formula of this class, usually you will do homework in the class, but sometimes I will assign homework for you to do. And we don't have exam, we don't have midterm exam, we don't have final exam. And pretty much your grade will be higher than 85. So your grade will be 85, between 85 and 95. So you don't need to worry about your grade. You should be fine. If you go to iLearning, see, this is Centuria microsystem design. This is the textbook, so it is on our iLearning. It's in the course material, lecture 1. So, do you have access to the course material on iLearning? So do you understand my English? Yes? Good. Yes, you do. Great. So because we focus on sensors, so in our world we have a lot of sensors. We have sensors everywhere, like microphone. So because when you use your cell phone, you need a microphone. Yeah, to talk, to receive your sound through the microphone and transmit to other cell phones. So microphone is the main sensor. And we need accelerometers. So in our car, if we hit the other car, there's an airbag to protect us. So if the accelerometer senses the acceleration change due to the impact, then the accelerometer will send a signal to the airbag for the airbag to explode to protect us. So we have accelerometers. It's also a MEMS sensor. And we have gyroscope. Gyroscope to measure the angular velocity. So if you fly on an airplane, as the airplane turns, the angle is going to change. So we need a gyroscope to measure the angular speed. Then we have pressure sensor. See, in our room, we have the temperature sensor. We have the air pressure sensor to sense the environment, the humidity, the temperature. So those are micro sensors too. So they are everywhere. And we have we have some actuators, the piezoelectric actuator. Like if we need to, like in the company, if they want to have a translational stage to translate the movement, like 1 micrometer, then we need the micro positioner. The piezo actuator can do that. Okay, so a lot of applications by MEMS sensor. So it's quite fun. Is a lot of things we can do, we can play with. See, on your cell phone or in your home, see your cell phone. Your cell phone and your home, because temperature sensor, pressure sensor, humidity sensor. In your car, we have accelerometer. We have a lot of sensors, because electric cars, everything is sensor, chip sensor. So in our city, yeah, we need the street light to sense the light intensity and to automatically turn on or turn off. See, and the grid, the power grid, with the sensor, we can control the, say, the power, like power on or power off. So you can think about it. You can have everything, already, or almost everything in this environment. We have all kinds of sensors. Or the temperature sensor, or we have camera, we have micro mirror to, even we can have a projector on your cell phone to project your like Word document to the wall. So those are the micro mirrors, also MEMS actuator sensor. And your game box, yeah, we can play games and you can sense your gesture and the voice, the microphone, and the touch sensor. You touch your cell phone, you turn your app on, off. So this is touch sensor. It's a force sensor. to sense the force or the rotation. So consumer products, electronics, we need a lot of sensors. See the touch sensor. These are all touch sensors. And acoustic means sound, the microphone applications. And see, when you run outside, you can put on your smartwatch to measure your heartbeat or to measure your body temperature. So those are also the sensor you can put on your body. And also axiometer, gyroscope, and compass. Yeah, to measure the direction of, like to use the magnetic field to decide your moving direction. Those are all the sensors to help us to have a happier life. Okay, environmental sensor. And also, see now we go wireless. So because you want to go wireless, you need to have this RF, radio frequency transmitter receiver. So we have the waveguide to transmit the radio frequency signal. Although we don't do that in our class, we will do simple sensor. And by the way, it's very important. It's small, and it is made on the microchip, like the small die here, 1 millimeter times 1 millimeter maybe. So here we put our sensors just in this small area, and a chip can have thousands of microsensors on it. So small size, large quantity, low cost is the characteristics, the advantage of the microsensors. So it's just like the Alice in the Wonderland. 爱丽丝梦游仙境. So, have you ever read Alice in the Wonderland? Like a girl, like in her dream, she went to the Wonderland and she met Black Queen, White Queen. Do you know that story?
Yeah.
Okay. You don't have that story? Okay. Okay, this for motion sensors, microphones. Okay, the projector. The light projected from the microchip. So projector applications. The micro device, micro mirror, this one. And the laser comes in and goes out. And this micro mirror can rotate and to reflect the light to different directions. This is micro mirror. But always we need the electronics. We need the IC chips with electronics, like amplifier, like to control the signal and to amplify the signal. So we always need this electronics, also low power. Because we use battery, we need to think about power usage. Low power consumption is a requirement. But we don't do electronics in this class. Okay, not only for car, not only for entertainment, but also in farming. we can have sensors to control the irrigation. And so we have smart sensors for farm and the city, control the light. And the smartphone is the navigation, or to give you all the route information. It's already, you use it a lot, a smartphone. So you can use your sound to control on off, use microphone, use transmitter. Okay, smart cars. Self-driving car with these sensors, right? You don't drive, but you rely on all these sensors to detect the direction, to detect the incoming cars, or to detect the pedestrians. So we need this, a lot of sensors for smart cars, for self-driving cars. Okay, all the applications for smart car. So see, this is the airbag. It's actuated by accelerometers. So it's for your personal safety. And for the acoustic comfort, like the microphone or for the stereo system. And assisted guidance, like self-driving car with these sensors to detect all the outside world. So MEMS for smart car. And say cell phone and smart glasses. You could say, you can imagine, and also wireless applications. The RF MEMS, RF, the resonators, also MEMS resonators, to be a filter for signal processing. This is smartwatch. So for this PCB board, we have this main sensor, and they put accelerometers and magnetic sensor to this chip, and on this PCB, then put this PCB inside your smartwatch. So smartwatch to fitness, to sense, say, heartbeat, or temperature, or calorie usage, but also RF sensors, radio frequency, wireless applications. Okay. So all these sensors, everything, they will be connected to work together. We call this Internet of Things. Like all the sensors connect through this internet. So this network, everything, main sensors, processors, and wireless. So this is the system. And different sensors for different applications. So for transportation, so for factory, and for personal fitness, and for healthcare. We just connect everything together, all the information flow in the air. So Internet of Things is just the networking of sensors to provide all the information. And we work here, main sensors in this whole network. An electrical engineer, they may work on the analog, the sensing circuit, and the processor, and the wireless, transceiver, transmitter. So electrical guys, they work here. Mechanical guys work here. Also, it's good to know something about circuit. It's good to know something about sensing mechanical structures. Then they can work together to make the Internet of Things. Okay, so far, any problem? Okay. So, so you could, so now what time it is? Can you turn off this? So silicon is our silicon wafer material. So now everything happens on silicon wafer. So belong to 4A family. But silicon is now, we want to turn it into a conductor, so we need to put either 3A family boron or 5A phosphorus inside the silicon to make the silicon to be a conductor. So if it's boron, remember, if boron gets in, the outermost circuit will have 4 electrons for silicon. The outermost orbit will have 3 electrons for boron. So boron, you can imagine silicon, 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 and 1 boron here. And silicon has 1, 2, 3, 4. But boron has only 1, 2, 3. So for this silicon, we have only 7 electrons on the outermost orbit. So there's one empty site. So this empty site, we can think is a positive charge. So if we put boron into silicon, now it's a conductor, and the carrier, the charge carrier, is a positive charge. But if we put phosphorus, remember we have 5 electrons in the outermost orbit. So imagine silicon, 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 and 1 phosphorus comes in. But phosphorus has 5 electrons. So 5 electrons, 1, 2, 3, 4, and we have 1 free electrons moving around to be the free carrier. So we use the electron as the carrier. So this is N-type semiconductor. If we put boron, it's P-type semiconductor. So this is the introduction of the semiconductors. But for MEMS, we use tungsten. This is the metal tungsten for conductor. We also use the gold as the pad to connect to the other wire. So aluminum, gold pad, and zinc and copper also. Copper, we also see a lot of copper in the MEMS design. And titanium, Ti also is very useful in the MEMS design. So important metals here, and binary, elemental, ternary semiconductors here. And ionic contaminations. These are the materials we don't want because it's contamination. It's going to deteriorate the performance of our MEMS devices. So they are the bad guys. And here are the good guys to the MEMS sensors. Okay, any question so far? Let me ask, for silicon to become the semiconductor, which 2 families we can add into the silicon to this is 1A, 2A, 3A, 4A, 5A, 7A, 6A, 7A. So which family we need to add to the silicon?
3A and 5.
Yeah, 3A elements and 5A elements to add into silicon to make silicon a semiconductor. Okay, ion contaminations. Okay, I would have. Martin, could you read the first point?
The mobile ions often enter the gate oxide through the interface between the gates, usually metal or polysilicon, and the gate oxide, usually silicon dioxide. Some of the ions can drift to the silicon dioxide interface under the influence of electric fields created by the voltage applied to the gate. Given the high mobility of these ions in silicon dioxide, they can drift under field assistance even at room temperature.
Yes, because for the PMOS or NMOS, if you don't have, for the MOS transistors, we have a gate, we have source, we have drain for transistors. It's okay if you have a picture in your mind. You just listen. You are fine. It's not a problem. So for a transistor, we have gate, we have drain, we have source. We have three head. Okay, they are conductors. But between the gate and the drain and source, we need some gate oxide. So the gate oxide, some ions from the 1A and 2A family, they are very active. See, 1A, 2A, they are active materials. It's easy to be influenced by the electric field in the semiconductor, in the transistor. So they may go inside. Because they are very mobile, high mobility, so they may get in to contaminate our transistor performance. So this is the ionic contamination from 1A, 2A families. So we have some transistor, the PMOS, NMOS concept here. It's okay if you don't have any picture, it's fine. Okay. Kaiser, could you read the second?
In the presence of these ionic contaminants at the gate oxide and oxide semiconductor interfaces and in the oxide itself results in a mobile ionic charge which can cause long-term changes in the threshold voltage of the transistor. The threshold voltage shifts aggravates as more charges accumulate at the silicon dioxide interface.
So VT, because transistor rely on this VT to operate, is a very important parameter. So if this VT change a lot, it's going to make your transistor fail. So this is the problem with the ions. So we don't want those ions. We want to prevent them. Okay, semiconductor, we'll skip. Yeah, in MEMS, these materials are very common. Silicon, see, silicon wafer. We create our device on silicon wafer. So silicon is certainly very important. Okay, then silicon dioxide, because for our device, we want some parts to be isolated. We don't want everything to be conductors. So this is the isolation, the isolators, the non-conductor silicon dioxide, because it's very easy to grow silicon dioxide on silicon. If you put silicon wafer in the air, we have oxygen. So naturally, the silicon wafer, there's a thin layer of silicon dioxide on the silicon wafer. So they are inevitable. silicon dioxide. And silicon nitride is a very good insulator. So sometimes we need to grow silicon nitride on the silicon wafer for our design purpose. But still, no, we may not use it. But sometimes we use steel wafer. We can do electroforming. We can use the chemical deposition, the electroforming or electrodeposition to grow, create copper or nickel structure on the steel wafer. So yeah, but we don't see them too often. The silicon dioxide, silicon nitride, see, and formers and diamond. This is the crystal. Not all materials are crystal material. Crystal means the atom arranged in a radial order. If the arrangement of the atoms is random, there's no regular structure, this is amorphous material. So silicon nitride, silicon dioxide, they are amorphous. There's no regular atom arrangement. But for silicon, it has diamond structure. So later I'll show you the diamond crystal structure. But you can remember silicon is a crystal material. And Young's modulus. Young's modulus is the relation between you apply a force to the material. It's going to elongate. And the relation between the force and the elongation is the Young's modulus. You can take it as the stiffness or the spring constant based on the Hooke's law. Okay, so yeah, Young's modulus, important material properties. And silicon is quite hard. It could be 190, 150 for polysilicon. So polysilicon means polycrystal. Means we have not only one crystal. Single crystal material means this material has only one crystal. But polycrystal means we have multiple crystals in the material. So it's polycrystal silicon, polycrystallized silicon. So we can call it polysilicon. So what is polysilicon? What is polysilicon? Bottom. Polysilicon. Lie.
The polysilicon. Maybe I don't know the characteristics, but I know the polysilicon when we use in the main design, we use it to transfer maybe some characteristics to hold the whole MEMS.
Okay, but poly. I just explained amorphous, crystal, and polycrystallized silicon, single crystallized silicon. So what I mean is, what I'm asking is polycrystallized silicon. So what is polycrystallized silicon means? Sorry, Stephen or Evan? Leo, sorry. So Leo, can you explain to me what is polysilicon? Polycrystallized silicon means, do we have single crystal or several crystals? Single crystal or multiple crystals? Hugh, what's your answer?
The polysilicon is mean we have several crystal in the structure or material, so we say it's polysilicon.
Yeah. So, Ami, could you repeat Hugh's answer? Do you understand? No? And okay, but we will explain detail later. Okay, we have several other material properties. So density and shear modulus, coefficient of thermal expansion. Coefficient of thermal expansion is if the deformation is, if we give heat energy to the material, it's going to expand. So this is the coefficient between the thermal strain and the temperature increase. We will get to that later. You'll have a better idea of these material properties. But when during our design, if you select different materials, you may need different material properties to calculate to design your device. Okay, for MEMS, we use metals and insulators, the silicon dioxide or silicon nitride. Or we use polymers, because for microfabrication, we need photoresist. They are polymers, like polyimide polymer. It's soft, it's like PDMS. So sometimes we use them, yeah, for our design, for our purpose. Then, yeah, certainly silicon. Okay, so these are some background idea. Here, see, remember what I mentioned about crystal structure. These are atoms. For amorphous material, these atoms, the arrangement are random. There's no structure. But see in this one, one atom are connected to 4 other atoms. And the angle are fixed. This angle are fixed. So this crystal structure, we call this type. There are many types. So for this type, it is diamond crystal. Silicon, germanium, these two important materials, they are crystals. And the crystal structure is diamond structure. So this is the diamond structure. So this is just one, we take one unit from this crystal. So this crystal structure, and something we need to know is the crystal's surface. See, for this crystal structure, you can think, so if we take this one is X coordinate, this one is Y coordinate, this one is Z coordinate. So if we find a surface passing through this, passing several atoms, so this is the surface, the color in red, the red color. We want to give it a name, but how we name this surface? Some guy, Miller, he created this Miller's index for this surface name. So we call this one 111 plane, because the normal vector to this surface, the normal vector, the vector perpendicular, vertical to this surface is 1, 1, 1, the vector. See, this is 1, 1, 1. So this is the origin. From origin, we have a vector go to the 1, 1, 1 direction. So this 1, 1, 1 vector is normal, means perpendicular, normal to this surface. So we call this surface 1, 1, 1 surface or 1, 1, 1 plane. Ami, do you understand? Can you repeat? Try. Give a shot. What is one? Why this surface is 1, 1, 1?
That's why we take time.
Huh? Again, please. Why this one is 1, 1, 1? Please.
1, between the last normal vector.
Yeah. Okay. Okay. Fine. Good. Okay. So why we care about different planes? Because during microfabrication, in the etching process, different planes have different etching speed. So, because 1, 1, 1 plane, you can think 1, 1 plane compared to 1, 0, 0 plane, or 1, 1, 0. So this plane 1. So if there's plane going through this one, this one, this one, and this one. For this plane, it is 1, 1, 0 plane. Because for this plane, the normal vector for this plane, 1, 2, 3, 4. The normal vector is in this way. So for this way, this vector is 1, 1, 0 vector. Afwan, do you agree with me? Yes. So this is 1, 1, 0 vector. So this plane is 1, 1, 0 plane. If there's a plane going through these 4 atoms, the normal vector is this one, from this node to this node. So this vector, so can I ask, so sorry, what's your name? Your name? Qingyou. So for this plane, the plane going through these 4 atoms, what is this plane? What is the normal vector going through this plane? The normal vector from this node to this node. Yes, 1, 0, 0, 0, 0, 1, or 0, 1, 0. They are the same. So this is 1, 0, 0 plane. So for 1, 0, 0 plane, and 1, 1, 0 plane, and 1, 1, 1 plane. Compare these 3 planes. We have 1, 1, 1 plane. It's another atoms compared to 1, 0, 0 plane or 1, 1, 0 plane. It has more atoms in this plane because it has more atoms. So the etching speed is slow compared to 1, 0, 0 and 1, 1, 0 plane. So 1, 1 planes etches slowly. And another way is 1, 1 plane has fewer dangling bonds. So you'll skip that. So the etching rate ratio exceeds 1,000. It's a huge difference. See, 1,000 to 1. The etching speed, 1 runs 1,000, 1 just runs 1 meter. So it's a huge difference, the etching speed. So if we use the different etchant the anisotropic agent, potassium hydroxide KOH, or ethylene diamine EDP, or tetramethyl ammonium hydroxide TMAH. They are anisotropic agents, means they can etch different atom planes with different rates. Okay. Some agents, they are isotropic agents. They will isolate everything with almost the same speed. So we have isotropic agents, we have non-isotropic, anisotropic agents, means the agent speed in different directions are different. Okay? So any problem so far? Any question? Okay, again, what is anisotropic agents? Martin, what is anisotropic agent?
This is a non-homogeneous composition.
Yeah, it's not uniform. Yeah, it has different aging speed in different atom surface. Good, good. Kaiser, what is diamond structure?
It's like crystalline structure. Crystal.
Yeah, it's this type of crystal.
Yes.
So in diamond structure, how many neighbors each atom has? Each atom has how many neighbors? How many atoms?
3 or 4 different. 4.
It's 4. It's not 3. It has 4 atoms as its neighbors. The bond, 4 bonds in diamond structure. Okay, so it's some interesting thing to know. Just for take it as fun. Okay. The dangling bond means on this surface we have some bonds, some atoms outside this surface connected to this surface. We call those atoms dangling bond. So okay. Okay, we mentioned 110 plane. So 涌泉, so 涌泉, 氢氧. So see 110 plane. See, if this is x coordinate, this is y coordinate, this is z coordinate. The normal vector is, say this vector is 110. Okay? So this is 110 plane. 110 plane. Okay, let's move on. Now suppose we have a silicon wafer. We have different types of silicon wafer. We have 111 wafer. We have 100 wafer. We have 110 wafer. How to differentiate different types of wafers? See, if a wafer, so when we create the silicon, it's a cylinder, and it's a single crystal material. Means the whole silicon cylinder, we only have one crystal inside. So for this single crystal silicon cylinder, wafer is very thin, 500 micron. the thickness for each wafer, only 500, 0.5 millimeter. But how are we going to cut? We can cut it this way, or cut it this way, or cut it this way, different cut. Different cut, we have different surface, atomic, atom surface. So if the surface of this silicon wafer, the normal vector to this surface is 1, 1, 1, then we call this wafer 1, 1, 1 wafer. Okay, so what's your name, please? Yes. 正义。正义。正义。正义。
一神一神。
哦，正义。
对。
好，正义。What is 111 wafer? 亲友。Okay, so Martin.
We can say in which all the three axes have the normal, in which plane all the three axes have normal to this plane.
For the atom, all the atom on this surface, the normal. Okay, let's go back to. See, if the surface of the wafer is this surface, the surface of the wafer could be any surface. It could be 111 surface. It could be 100 surface. It could be 110 surface. It's possible, depends on how you cut the silicon cylinder. So if the surface happen to be this surface, then we call this silicon wafer 111 wafer. So Zhengyi, do you understand? Yongchen, how about you? Can you imagine? Barely? So Kaiser, can you imagine the 111 wafer? Do we have a picture? Okay, so what is 111 wafer? What? Watch it.
In the wafer, the cell is 111 surface.
Okay. Yes. The 111 wafer means this surface is 111 surface. Okay. So we know that the etching rate 111 is the slowest. This is positive feedback. Okay, remember we have 111 surface, but in this 111 surface, it could be 1 minus 1 surface. It could be 1 minus 1 surface. So let me explain a little bit. Okay, for this one, let's say this surface is 100 surface, because if we take this is x, this is y, this is z. So this surface is 1, 0, 0 surface. Do you agree with me? And if this is x, this is y, this is z, we can do it this way. We can select any coordinate system. So if this is x, this is y, this is z. So now this surface becomes 0, 0, minus 1, because the normal vector. So for this surface now, this is x, this is y, this is z. So for this vector, it is 0, 0, minus 1. Right? Zhengyi, do you agree? Yeah, 0, 0, minus 1. So we call this surface 0, 0, minus 1 surface. But you can think, how come it's 1, 0, 0 before? Now it becomes 0, 0, minus 1. Actually, it could be if this is y, this is x, and x. So if you choose this one as x, y, x, y, z. So x, y, z. So this surface becomes 0, 1, 0 surface. So which means 1, 0, 0, 0, 1, 0, 0, 0, minus 1. They are the same surface. Do you? Okay, let me ask. Okay, what's your name, please? Yes. Minjun. Yunjun. Okay. So see, we select different coordinate systems. For different coordinate systems, this surface could be 1, 0, 0, 0, 0, minus 1, or 0, 1, 0, which means they are the same one, right? They are the same one, but they have different names. But their names are 0, 0, minus 1, 0, 1, 0, or 1, 0, 0. You see, there's only one there. The other two are zeros. And it could be positive, it could be negative. It doesn't matter. So means 1, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, minus 1. They are in the same family. They are the same surface. Okay. So, which brings me to this. For 1, 1, 1 surface, it's also a family, like 1, minus 1, minus 1, minus 1, 1, minus 1, 1, minus 1, minus 1, minus 1, minus 1, minus 1. They are the same. Just some minus signs. So let's come to this one. So this surface is 1, 1, 1 surface. But also this surface also belongs to 1, 1, 1 surface. You can imagine. It could be 1, 1, 1, and so this one could be, you see, this one and this one. They are just the same surface. If the second wafer this surface and this surface, they are, it could be, so this one could be 1, okay. But anyway, let's say okay, DRIH For DRIEH is reactive ion etching. We use the high-speed plasma. You can think the gas, high-speed gas with very high-speed ions. Just heat the second wafer. So for reactive ion etching, it's going to just go deep. It doesn't matter. It just go through this direction. You can think you are doing the milling. You just mill, go deeper and deeper. It's reactive ion etching. But we just stop here, we stop here. Then after that, we use anisotropic etching. Anisotropic etching. Now, different atomic surface has different etching speed. Remember 111, etch very slow. So this is 111 surface. So if you want to go deep, very difficult. It's easy to go sideways. So for the etching, go here and go sideways. Go here and go sideways. And this one, go down a little bit, but go sideways a lot. So eventually, it's going to have a cavity look like this. The etching speed in the 111 atomic surface is very slow, but the etching speed in this direction and this direction is much larger. So that's how we get this cavity this way. So due to the anisotropic etching, undercut, and this is DRIE is just etching this way. Only one direction. This is DRIE etching. So Minjun, are you Minjun, right? Huh? Yunjun. Do you follow me? Good. What time it is now? Okay, 3:20. Let's have 10 minutes break. Let's come back around 3:35. Okay? Let's have a break, 20 minutes break. Okay. Then, if this wafer is 100 wafer, means Zheng Yi, would you mind to come here, please? Yes. So 100 wafer. So this is the wafer surface. Wafer surface here. So which plane is 100 plane? Which one? We have, so which one? This one. This one, and this one, and this one, and this one. All 6 planes are 100 planes. Yes. Yeah, right, yeah.
Oh, okay.
Because 100 wafer means the top surface must be 100 plane. But this plane is also 100. 0, 1, 0, 0, 0, 1. They are all 100. Okay, if this is 100, so this one is 111. This one is 111. 111, 111. The green surfaces, they are 111. And remember, 111 has very slow etching rate. So if we etchant, anisotropic etchant comes from the top, eventually you will have a V-shaped cavity inside the wafer. And this is 111 plane, 111 plane. And the angle, because this is 111, and this one is 110. 110, 111. We have two vectors. One vector, and this vector is 111, and this vector is 100. You have two vectors. You can use the inner product A vector dot inner product B vector equal to length of A vector times length of B vector times cosine theta. Theta is the angle between vector A and B. You can use this to calculate the angle between two vectors, 111 vector and 100 vectors. And you can calculate 54.7 degrees. Or your answer could be 54.7, it could be 3.5.3, because then you'll get two answers, because one angle is and the other angle is the other one. Yeah, two vectors. So one vector here, one vector here, you are going to get two angles. Your solution depends on the direction of your vectors. I can do some calculation here. Inner product 1, 1, 1 equal to square root length A times square root length B times cosine theta. So theta. Anyway, that's the equation you can use to calculate the angle. Yeah, because 100 inner product. So this one is 1 times 1 plus 0 times 1 plus 0 times 1. So this inner product is 1. Well, just so for 100 wafer, so it's good. We put anisotropic agent to H. This is 111 plane. This one is 11 plane, and the angle is 54.7 degree for anisotropic agent. And this one is silicon dioxide. So this one is the opening. This one is the opening. For large opening, you go to H and stop at 111 plane, 11 plane. Stop at 111, 111 plane. Okay. So use this technique, we can create pressure sensor. Then we can etch from the bottom. And this is 111 plane, this is 111 plane. We etch from the bottom. and stop here. We can use for some materials, like the previous slide said, if we put the if we put boron inside the silicon, the aging rate is very slow. But if this is boron, the membrane here, if we put another boron here, when we etch from the bottom, this is 111 plane, 111 plane, very slow aging rate. And here it reached this area, but this area is used boron doped silicon. We put another boron there, so the flow rate, age rate is very slow. So it's going to stop with the boron heavily doped. So this is the membrane, the thin film. We could use this thin layer to create a pressure sensor. Like this one. And we can put piezo layer. Piezo layer means if there's a stress here, it's going to have a voltage output. Or if this is piezo resistor, if there's a stress, the resistance is going to be different. Piezo resistor. Okay, you'll learn that later, so don't worry about it. So just think, if there's an air pressure here, we are going to deform this membrane. Due to the deformation, the piezo resistor, the resistance will be changed. If the resistance is changed, the voltage output is different. So we can use this property to measure the air pressure inside. So, sorry, what's your name? Yu Qian. Yu Qian. Okay, Yu Qian. Do you know the principle of this pressure sensor? So, what's the surface of this one? 100. If this is 100 wafer, so what is the surface of this one and this one? 100, 110, 111. Yes, because 111 has the very slow aging rate. And if we put boron on this surface, the age is going to stop in this layer, boron heavily doped layer. So this is we can use the wiring to wire these 4 piezo resistors this way. And this one is the crystal bridge. We can get the voltage output. So this is voltage source. This is the voltage output due to the resistance change of these piezo resistors. We will get into that if we have time when we introduce you the pressure sensors. We will discuss more about this. So, yeah, you can have some piezo resistors, the dummy ones, outside this layer. For these two are the dummy resistors. Its resistance won't be changed, but these two resistors, their resistance will be changed due to the air pressure inside. So these two may be these two resistors, and these two might be some dummy resistors outside this diaphragm, this thin area. So if we have this voltage in, and this is R, and due to the variation of the resistance, this is R plus delta R plus delta R. So this is voltage output. So delta V will be equal to delta R divided by, say, 2R times the source voltage. So delta V due to the delta R. So if you know delta V, you know delta R. If you know delta R, you know the pressure inside. So this is the concept of pressure sensor. So 涌泉、清泉、涌泉、清涌。Do you understand this pressure sensor? Operational principle. So, okay. So another MEMS device. That one is pressure sensor, and this one is the inkjet printer to push out the ink for the printer. See, this is the ink, and ink goes in and from this nozzle, so high pressure goes out for printer applications. And we use microfabrication to create the V cavity or this cavity. Use the anisotropic etching process, and we push the ink get in and get out from this nozzle. And if the actuator, we use ultrasonic, like 20 kHz vibration of the ultrasonic actuator, then we can have high frequency ink coming out from this inkjet printer. See, this is inkjet ZET printer. Okay, so another application of the MEMS technology. Okay, so here are the summary for today's introduction of the machining. Bulk micro machining is we remove material from the silicon wafer. This is bulk micro machining. We have different technology to carry out this bulk micro machining. So how many of you have taken the course Microfabrication in our department? 微制造工程 Microfabrication. Have you? No, not yet. Have you taken the course Microfabrication? So did you learn this bulk micro machining? No memory. Nothing. So Zheng Yi, have you taken 微制造工程? Not yet. Yes, but did you learn this bulk micro machining in the 微制造工程? Okay, good. Another topic is surface micromachining. So bulk micromachining means we remove material from the silicon wafer. But surface micromachining means we put a lot of thin layers on top of the silicon wafer. So this is surface micromachining. Say we have silicon wafer here, then we put silicon nitride, then we put polysilicon. Then we can remove the polysilicon here and put silicon oxide. Then we remove the oxide here, we put the polysilicon poly 1. And then we just put different layers, layer by layer, to create micro device. This one is a micro rotor. So this is the cross section, and it's a micro rotor. See, different layers has different thickness. So this is a MEMS, multi-user micro-machining process. And like TSMC, Taiwan Semiconductor, they have different surfaces for different processes for the users to use it. And they all have the rules for different layer thickness. And the anchor, the different layer, different names. Okay, just surface micromachining means we put layer by layer on top of the silicon wafer. See, this is what I mentioned. This is the rotor device. So after the micro machining process, in the end, we got the device like this. Then we have oxide. We remove the oxide. We can use HF etching, the oxide etching to HF to remove the oxide. If we remove the oxide here, we remove the oxide here, we are left with the polysilicon structure. Polysilicon. And this is metal, tungsten metal, or aluminum. Then this is the cross-sectional view. So this one is the rotor. This is the center. And this rotor can rotate. This is micromotor. Can you imagine this? Okay. Again, could you imagine this is a circular rotor? And because it cannot flow, so we have a small tip touch the ground. So we have some friction between this rotor and the surface. But yeah, it's a micromotor, electrostatic micromotor. We can use like electrostatic field to drive this micromotor. Okay, Master, what is surface micromachining?
It's the addition of layer by layer.
Okay, good. Micro mirror. Reliability. Micro turbine, also micro motor. Micro mirror. Okay. Remember, for any mechanical structure, we need the circuit. We need the circuit to sense to have the voltage output. Because the voltage signal, probably we can use all the electronic instruments to measure the output. So we need voltage signal output. Then the micro device is very small. Pressure sensor, if the signal output very small, we need to have the circuit to amplify the small signal. So we need the circuit, we need amplifiers. But we also need filter because we have a lot of noises. The noises from our power source, from the temperature, from the vibration, or from the circuit. We have a lot of noises. So we also need a filter. So we need a lot of electronic device to help the sensor to get the signal out. So we need CMOS, the MOS device, the metal oxide semiconductor, or complementary means we need NMOS, we need PMOS. PMOS plus NMOS is CMOS, means complementary. P and N complement each other to form complementary MOS device. So MEMS plus MOS is a complete system. So yeah, so we have Motorola. So Berkeley University, they have this comb drive. They have the CMOS microprocessor. Okay, CMOS here. And the MEMS here. Berkeley. And Elo Devices, very huge company. So their device, the circuit everywhere. And MEMS. And Intel. So the varactor, the MEMS inductor here, and the CMOS chip and the inductor here. So CMOS plus MEMS. Or Motorola. See, this is the MEMS device, and it's in the chip. And this is IC. We have different small chips on this IC. Yeah, but so in this case, we have several electrical engineers, we have several mechanical engineers, and you are optic engineer or material engineer. Sorry, who are正义 who is your advisor? Your 教授 advisor? 哦，林老师，永泉 ，right? 林老师，who are your advisors? 林老师，林老师 ，OK， 王老师 ，OK， so 林老师 also so what are your research topics? 你们的研究题目大概是哪个方向？你们4位研究的大概主题？啊？也是做微机电吗？
就是应该是残留应力。
哦，残留应力就主要是 OK，so it's also material science, maybe mechanical, yeah, residual stress, so 4B, thin film stress, residual stress. Okay, all right. So residual stress is also because main structure will deform after fabrication due to the stress inside. So yeah, it's also very important topic. Okay, so we run out of time today. So that's what we will do. And please